shading models. So now that we have transformed our geometry and projected onto the screen, we want to shade our faces, our triangles, our cubes, our tables with the correct colors. And what are these correct colors? So we would want to calculate some sort of a light that is hitting the surface, a 3D surface, and then we want to see these shapes shaded in this 3D way. Now there are three shading schemes, as we can call them. We can distinguish like flat shading, so this is where each face of our geometry gets its own shade, so this kind of a low poly look. Then there is something called the corrode shading model. This is where we calculate the light in each vertex, so in the vertex shader. So all these vertices get a color value, which is then interpolated across the face. And then the Phong or per fragment shading scheme, where the light is calculated per fragment. So each fragment calculates its own shade. Now, while I've called this like the Phong's shading scheme, there's actually something called the Phong's lighting model, which we'll see later on, and what Phong is more known for. But in his paper, he also described this per fragment shading. So basically, when people talk about Phong, they usually talk about the formula, which we'll see later, on how we calculate lighting, not specifically where. So this is more commonly known as per fragment shading, per vertex shading, and per polygon shading. And well, you can see this example also from Scikit-learn. So we have this flat shaded sphere and cube, and this per vertex shaded sphere and cube, and per fragment shaded sphere and cube. So those cubes look very similar, but those spheres, you can see, well, this is clearly distinct, but you can also see a distinction between like this sphere and this one. So the right one is a lot more smoother. Now this flat shading, the first like simpler one, each face has this one uniform color shade. So we have some vertices, we have some fragments. So these fragments are basically pixels that are projected to a screen of the face. So those all along one face have a single color. Now in the modern pipeline, this is a bit tricky to achieve, because if you want to have one color across one face and a different color across the face next to it, then we would have to duplicate these vertices. This vertex, the pink vertex here, would have the same coordinates, positional coordinates, as the red vertex, but its surface normal would be that way. So that when we calculate light, then it would calculate this pink shade, while this other vertex would calculate this red shade, and then you would have like a uniform red face next to a uniform pink face. The next shading model, this corrode shading or per vertex shading, also calculates the color per vertex, but now the color is interpolated across the face, and each vertex calculates a different color. So this vertex would calculate the color according to this surface normal, so maybe it's a bit darker red, and this one calculates it according to this surface normal, so it's a bit brighter red, and then this color is interpolated, so it changes from this brighter pink all the way to red and then to dark red along the face. So the light calculation is performed at every vertex. You get a color from each vertex, and then the colors are interpolated and kind of mix across the face. With Phong shading or per fragment shading, we interpolate the normal vectors. So with corrode, we interpolated the color and calculated it in the vertices. So here we don't calculate the color at the vertices. Instead, we have a surface normal per vertex, but we interpolate this surface normal across the face. So every fragment here has its own surface normal, which is an interpolation between the surface normals of the vertices, and this is which gets you this smooth shade, because every fragment thinks that there is this nice curvature going on along this face, while in reality the face is actually flat. So the lighting calculation is performed at every fragment. One thing you should pay attention to is that if you just interpolate normal vectors, then these will not be of unit length. Because imagine like if you have a normal vector 1, 0, and another normal vector 0, 1, you find the normal vector exactly between them. That's 0.5, 0.5. And if you calculate its length, well, that's not 1. So when you do that, you actually have to normalize the interpolated normal vectors in the fragments as well. So if a fragment gets in as input the interpolated normal vector, it's not of unit length, so you have to normalize it, and then you can use it in the lighting calculations. So from this video, you should understand flat shading. So each face has one color. Gouraud shading, so every vertex has one color, and colors are interpolated across the faces. And the Phong or per fragment shading, where the normal vectors are interpolated across the faces. The normal vectors must be renormalized, and then each fragment calculates its own color or its own shade from the interpolated normal.